In this video, I'm going to talk about arc length. Now, the concept of arc you've seen before, in particular, geometry might be a place where you've seen it. Typically, they talk about it when they talk about circles. And then here, let's say we have this like wedge of the circle. The arc length is the length along that outer edge of the circle. Okay. So often most people have kind of dealt with arc length before. It's the idea that we're finding the length of something that's curved. So like figure one here would be an example of something we want to find arc length of. But of course, figure one, if I were to visualize this in the Cartesian plane over the XY axis, this is not a function. Okay. And since it's not a function, we have some problems with that. Now, not to worry, well, we solved that problem by introducing parametric equations. Now, you probably went through parametric equations back in trigonometry, but if it's been a while, section 1.7 in our book does some really good examples, like right off the bat, that kind of gets you used to how parametric equations work. The idea is you have two different equations for the XY coordinates. So these two equations are feeding these ordered pairs, which end up mapping out these kind of interesting figures, right? We get these like points on the figures. And maybe this is where t equals 0, and this is where t equals 1, and this is where t equals 2, right? The idea is that it's mapping out these curves for different t values. It's a common t value, though, for the x and the y. Okay, so suppose we have some parametric equations that create a curve that look like that. Figure one here, we have it down here. And we want to find the arc length. So what do? We do what we've been doing over and over again. We're going to break it up into smaller geometric figures that we're more comfortable with. Okay. In this case, we're going to do line segments. Now, if I wanted to find the length of a line, that's super old school. That is distance formula. And if I wanted to find the distance between 2 points, so let's say the point P, which is x1, y1, and the point Q, which we'll call x2, y2, that distance is given by the square root of x2 minus x1 squared plus y2 minus y1 squared. Here, I'm going to zoom in a little. It's kind of small. Difference in the x's plus the difference in the y squared. It's basically a play on Pythagorean theorem, right? It's using the Pythagorean theorem to help us find the length of that line. All right, so we're going to use the distance formula to do this. Before I do, I want to introduce a notation. You probably have seen it before, but just in case you haven't, like this specific line segment here, if I wanted to write that in like a special notation, I would use P sub I minus 1 to P sub I. So those are the two endpoints, and then put the like absolute value marks around it. We're not thinking of them strictly as absolute values. We're thinking of it as a length between those 2 points. The word magnitude also gets thrown around using that. And you might recognize that word from trigonometry. Okay, so we're going to use that notation to represent the length of the line between P sub I minus 1 and P sub I, which I picked on purpose because that's the ith one. Okay, so if I wanted to use the distance formula to do this, P sub I minus 1 times P, I'm sorry, not times, P sub I minus 1 to P sub I, that line segment can be found formula, but rather than using ordered pairs, I'm going to call the difference in the x's delta x. And then the difference in the y's is delta y. All right. Now, we're going to cheat a little bit here, and we're going to use the concept of derivative. So I'm going to use f prime of t as my notation, and I'm kind of stealing from the notation up here for this parametric equation. Okay. So f prime of t, actually not equals, approximately equals delta x over delta t. All right, delta x over delta t. It's the difference in the x's over the difference in the t's, which makes sense because remember, this is the slope of a line. So we're talking about finding the difference in the x values over the t values. Okay. So if I wanted to be clever, I could write then that delta x is approximately equal to f prime of t delta t, right? Solving for delta x. Okay, so I'm going to plug that up into the distance formula here. And oops, that's got to be approximately equal to f prime of t delta t squared instead of delta x. And then instead of delta y, I'm going to use the notation, for the parametric equation for y, which was g. So y, delta y could be thought of as g prime of t delta t. So here's what's nice about what we just did. We got it into the same variable. Okay, now we're only working with t, and that makes our life a little bit better. Plus, we got some derivatives, which we like. We like derivatives. I'm going to do a little bit of simplification, which basically means I'm going to take the delta t and I'm going to square those just individually away from the f prime and the g prime and factor that out. Actually, here, I'll take a second and write it. Hopefully I have enough room. Oh, technically is approximately equal. Approximately equal to. Okay, so here, I'm going to do what I call blackboard magic. So if I write that squared times delta t squared plus g prime of t squared times delta t squared. So they both have a delta t squared in common. Okay, so here's where I'm going to do a little bit of magic just because of space. I just don't have a lot of space. I'm going to factor that out, that delta t squared, and then take the square root. So it actually comes out of the square root. Okay, so this actually, here, let me write what it actually equals then, simplified. And rather than have a bunch of parentheses, that looks stupid. It's f prime of t squared plus g prime of t squared at times delta t. We're going to take all these line segments and add them up. All right. And when I add them up, the whole purpose of that is so that eventually I can take a limit. Oops. Sad little sigma. Wow, I'm just struggling with sigma right now. Here we go. There we go. So I'm adding them all up. Squared g prime of t squared delta t. And then I'm going to take the limit. And what happens when I take the limit, I'm going to do called the surreal limit. I'm inserting a limit in here. The limit as n goes to infinity, as we're assuming n line segments, right? Because it's p sub n is the last point there. As n goes to the length from p sub 0 all the way to p sub n, which they call L for arc length, ends up equaling the integral from a to b, and that's coming from our limits on t up here in our parametric equation, from a to b of the square root of, and then they actually switch, instead of saying f and g, they switch into Leibniz's notation of dx dt squared plus dy dt squared That way they're not being specific to a actual function type, but just referring to whatever equation we're using for x and whatever equation we're using for y, and no longer delta t, but now dt. And there we go. There is our equation for finding arc length. Not too bad. And here it is. Nice and clean right from the book. Okay, so let's go ahead and look at this example here. Let's find the arc length of this curve given by x equals t squared and y equals t cubed. Now, just really quick, just because I want to show you how the parametric equations work. When t equals 0, x would be 0 and so would y. So this point right here would represent t equaling 0. When t equals 1, x equals 1, and so does y. Oops, I forgot the equal sign. And that happens to be this point right here, which is t equals 1 now. So this is t equals 0, t equals 1. Okay, t equals 2. And at t equals 2, x equals 4, y equals 8, and there, that's this point right here. And as you can see, what we're doing is just, I'm showing you where these magical ordered pairs are coming from, where this curve is coming from. This is all coming from plugging in values of t. And if I wanted to find points in the middle, I could plug in decimals like 0.5 or 1.5 or 1.3, you know, whatever we want to plug in. All right, so that's where the curve is coming from. If it's been a while since you've seen parametric equations, or if you haven't seen parametric equations, that's how they work. They're not very complicated. Okay, let me erase stuff that I just put here. And let's go ahead and find the arc length for this specific example between 1, 1 and 4, 8. Now, actually, I just kind of solved a problem there for us. I figured out that at 1, 1, t is equal to 1, and at 4, 8, t equals 2. And that's going to be useful for setting up my integral because a and b is based on t. So the integral from a to b, and then the square root of, okay, so dx dt means I'm going to take the derivative of the x equation, which would be 2t squared. Dy dt would be the derivative of the y equation, which would be 3t squared dt. All right, so let's clean this up. So this is the square root of, oops, sorry, forgot the integral. Not a to b. Oh, that's so funny. I meant 1 to 2 because I know what t is. 1 to 2. There we go. 1 to 2. All right, so that's 4t squared plus 9t to the 4th dt. All right, so I can simplify this square root by pulling out a t squared, and the t squared will actually come out of the radical as just t. And that's actually useful. Oops, that t squared is gone. So that's just 4 plus 9t squared. Okay, here's why it's useful. I can do u substitution to solve this. So u could be 4 plus 9t squared. Then du is 18t dt, which means I could solve for t, since I have t sitting here and dt sitting here. So 1/18 du equals t dt. Okay, so in place of t and dt, I'm going to write 1/18. I just have a square root of u, and then I'll put the du at the end. And then let's go ahead and figure out my new integrands. So when t equals 1, and t equals 1, u is going to be 13. And when t equals 2, 36, 40, u will be 40. So 13 to 40. All right, let's take the integral of that, or the antiderivative. So square root is u to the 1/2. And here, I'm going to give myself a little bit more space and put it over here. So u to the 1/2, the antiderivative would be 2/3 u to the 3/2 times 1/18 still, going from 13 to 40. And I can already kind of tell this isn't going to simplify very much. Okay, but the 2/3, 2 goes into 18, gives me a 9. So 1/27th. And then 40 to the 3/2. Actually, 3/2 is the square root cubed. So it would be the square root of 40 minus the square root of 13 cubed. They do simplify this. The square root of, when you square root something and then you cube it, basically that means you're multiplying by itself 3 times, right? So 2 of them are going to get rid of the square root, and then we have 1 square root left over, right? So square root of 13, that's actually just going to simplify into 13 square root 13. I'm sorry, square root of 13 cubed is going to simplify into 13 square root of 13. That would kind of be the same for the square root of 40, except, so here, I'm going to write it, but don't write it. Just stay there for a second and listen. Square root of 40 is 40 square root 40, but 40 actually can be simplified further because there's a 4 inside there. I can pull the 4 out of the 40 out and take the square root of it. So the square root of 4 is 2, which I'm going to multiply by the 40, and that's going to give me 80. And then because I factored out a 4, that's just a 10 times 1/27. So that's as simplified as I can make it. I would be, personally, myself, would have been just fine with this, okay? But that's okay. That's how they would have written in the book, it's simplified form. Okay, let's kind of see what happens if we aren't working with parametric equations. What if we have something that we can represent with a function? In that case, we can create a parametric equation by just letting x be itself. Just say x equals x, and then y equals f of x. So that's kind of like an easy way of doing it. So here, just let me give you an example. So let's say y equals x squared. That's the function we're working with. In order to make it a parametric equation, I can say, well, then x equals x. Or if I want to be cute, I could turn it into a t, say y equals t squared, and then still x would equal t, whatever t is. That's just how you kind of manipulate it. But what that does is, if those are our two parametric equations, that does change the way the formula looks. The formula then becomes the integral from a to b of, instead of it being dx, right? That would be how you'd write the derivative in terms of x with respect to x. It's going to just be a 1. Derivative is going to come out to 1. Squared, which is just 1, plus squared, all in terms of x. So it's possible to write it in terms of x. Or similarly, if we wanted to do the same thing, but maybe x is f of y, then we could let y equal y, and then our arc length formula. Again, we can just say from a to b in general would be dx dy squared plus 1 squared dy. I'm just not writing squared because 1 squared is 1. All right, here. Let's look at an example with that. Okay. All right, so let's say our formula is y squared equals 4 parentheses x cubed. Okay, so I could probably solve this for y. Just say that y equals, and then the square root of this, 2 for the 4, and then I'm gonna be clever, and rather than write square root, I'm gonna go ahead and write 3/2 because I'm gonna probably have to integrate this at some point. and that might help me. But you can put the square root. There'd be nothing wrong with that. All right. So there's my y value. Now I don't have an x, so x, I'm going to use the formula the first one right here. It's just going to be a 1, and I'm going to find dy dx. Okay, so let's do that really quick. Dy dx would be 3/2 times 2 x plus 4 to now the 1/2. Technically times 1 for chain rule because they're the derivative of the inside is 1. Okay, which is just 3 times x plus 4 to the 1/2, or the square root of x plus 4. Cool. But in the formula, when I square that, that ends up canceling that square root. So that's kind of nice. Okay, so the arc length. All right, x is ranging from 0 to 2 is the square root of 1 plus, okay, so this formula, 1/2 squared dx. Okay, so that's just going to be the integral from 0 to 1, square root of 1 plus 9 times x plus 4. That just basically gets rid of that. 9 for squaring the 3, distribute. So that's going to be 9x plus 36 plus 1 is just 37. 0 to 1. Okay, and then we could just do a simple u substitution. 9x plus 37. du is just 9 dx, or 1/9 du equals dx. So solving, putting that in, I'll put the 1/9 out in the front. I'll change the integrands in a second. Square root of u du. All right, let's change these integrands. When x equals 0, u is 37. When x equals 1, u is, see, 9 plus 37 is 46. Oh, I just realized. 2. That's a 2. Sorry, that's a 2. Sorry, I was double checking my numbers. That's a 2. Cool. Okay, sorry. Wow, 37 times 2 is 54. Wait, 37 times. Yeah, I'm doing that right. No, 9 times 2 is 18. 18 plus 37 is 55. There we go. Wow. All right. So that matches now my numbers. So u goes from 37 to 55. Okay. Antiderivative. So u to the 1/2 becomes 2/3. U to the 3/2. 37 to 55. No simplifying on that. That's just going to be 2 over 27. And then that's going to be 55. Okay, so we're going to have the same thing we had earlier to the 3/2 minus 37 to 3/2. So actually here, that's just going to simplify to 55 square root 55 minus 37 square root 37. And that's it. That's done. There's nothing more to it. And that's arc length.